Hi guys, today we are going to discuss the topic of T-beam of the subject Elementary Structural Design 6M Civil Engineering. Myself Assistant Professor Gaurang Prajapati from Civil Department MGTER Navsari. Introduction. So introduction of T-beam is if the flange projection are on the either side of the rectangular web or rib, the resulting cross section resembles the T-shape and hence it is called a T-beam. Now we can see in the figure over here it is highlighted as T-beam. Now talking about L-beam, if the flange projection is on the one side, the resulting cross section resembles an inverted L and it is termed as L-beam. Now if you want to highlight it, it is over here. In other language I can say all the intermediate beams are known as T-beam, while all the beams which are provided at the corner are known as L-beam. Now, concept of T-beam. For the concept of T-beam, we should understand that T-beam is nothing. It is the combination of singly reinforced rectangular beam plus slab portion. Now, as we can see over here, this one. Say this is nothing but the typical singly RC beam is there, while this one it is a slab portion of there. Okay, now if we combine these two, it will ultimately become T-beam. Now talking about T-beam, its dimensions are BF, that is width of flange, then DF, that is depth of flange, capital D overall depth of beam, while BW, that is width of web or rib. Now talking about the formula of that one, first of all this one. Now this singly reinforced rectangular beam, if I want to find out its formula, then it will be simple. As it is a rectangle portion, its area will be D multiplied by BW, that is we can see over here. While talking about the slab portion, now as this central portion is deducted from the slab portion, the overall dimension was BF. Now the central dimension BW has been reduced from it, so the remaining length will be BF minus BW multiplied by DF, that is shown over here. Okay, so if we want to understand the basic concept of T-beam, say formula of the overall T-beam, then T-beam equals to singly reinforced rectangular beam plus slab portion. The formula will be BW minus T, that is of the beam portion, plus BF minus BW multiplied by DF, that is of the slab portion. Now stress strain diagram for the T-beam. Now talking about the stress strain diagram, as I said previously also, T-beam is the combination of singly RC beam plus slab portion. So the strain and stress diagram will also be similar to the singly RC beam. Now talking about the strain diagram, it is exactly same as of singly RC beam, as T-beam is a combination of singly RC beam plus slab portion. Now talking about the stress diagram, first of all force C1. Now as force C1 is the force of compression of the singly RC beam, it will act at the same place, say 0.42 XU from the top of the beam, while force C2, that is over here, that is the compression force acting in the slab portion, it will act over here in this slab at the center, say at the depth of dF by 2 from the top. As two compression forces are there, C1 and C2, so two lever arm will be generated, Z1. Now talking about this Z1, the overall depth, that is small d, minus 0.42 XU, that will give us Z1. Now talking about Z2, overall depth d minus dF by 2, that will give us Z2. Now notation of the diagram that we already discussed, say BF width of flange, DF depth of flange, BW width of web, small d effective depth of beam, capital D, that is overall depth of beam, AST area of steel, XU, that is depth of neutral axis, C1, that is force of compression in concrete, that is we can say of beam portion, 0.36 FCK BW into XU, C2 force of compression in the slab, that is of the slab portion, 0.446 FCK BF minus BW into DF, T, that is force of tension in the steel, 0.87 Fy AST, Z1 lever arm, that is D minus 0.42 XU, Z2 small d minus dF by 2, FCK compressive strength of concrete, while Fy yield strength of steel. Now talking about neutral axis. Before getting the content of neutral axis, we should understand the two forces will make bigger impact on the position of neutral axis for that one. Those two forces are, first one Fc, that is force of total compression, 0.36 FCK BF into DF, while other force is force of total tension, that is 0.87 Fy AST. Now talking about the condition that well neutral axis will be lied in the T-beam. So first let me draw a cross section of T-beam, say this one. Now talking about the first condition, if Fc is greater than Ft, neutral axis lies in the flange. So for that one, if neutral axis lies in the flange, then neutral axis will pass over here, something like this. Now this depth is known as XU, okay, and DF, that is this depth, this one is our DF. Now from the figure we can easily understand the condition will be XU is less than DF. Now talking about the second condition, so again first of all let me draw a T-shaped diagram. Now condition says that if Fc is less than Ft, neutral axis lies in the wave. Now this one is wave, so from over here neutral axis will pass. So this depth is our XU and this one is our DF. Now from the figure we can easily understand that XU is greater than DF. Now talking about the third condition, again let me draw a T-shape first of all. Now if Fc is equals to Ft, neutral axis lies at the junction of flange and wave, means it will pass over here where flange and wave meets. Now this one is our XU, while at the same time this one is our DF also. So from the figure we can easily get that XU equals to DF. So friends, hope you got the idea of where neutral axis will lie and how conditions will be generated using the figure. Now depth of neutral axis is also one of the variable in this one, say as we already discussed about the different conditions of Fc and Ft. Now if Fc is less than Ft, neutral axis lies in the wave, that is the second case. If this condition arises, we can find out Xu using the formula C1 plus C2 equals to T, where C1 that is 0.36 FCK BW into Xu, C2 that is 0.446 FCK BF minus BW into DF equals to T, that is 0.87 Fy AST. Now in this formula Xu will be unknown and we can easily get the value of Xu, but mind well the Xu which we deduct from the above formula must be greater than DF, and if it is not greater than DF, then we need to find out the new Xu by putting YF equals to DF in this formula. YF is instead of this DF, where YF equals to 0.15 XU plus 0.65 DF. Now by using this formula we will get new XU and that will be definitely greater than DF. Now flange width. Sometimes flange width are not given in the data, so for that one we can find out flange width also using the IS code. Now flange width of the T-beam can be found out, say BF equals to L0 by 6 plus BW plus 6 DF. It is given in the IS456 page number 36-37 close number 23.1.2. Similarly we can find out flange width of L-beam also using the formula BF equals to L0 by 12 plus BW plus 3 into DF. It is also given in the same clause. Now in the above formula there are some of the unknowns are there, where L0 equals to distance between the points of zero moments in the beam, that is in other words I can simply say it is a effective span. DF that is depth of flange and BW that is width of wave. Now talking about the basic concept of T-beam analysis. First of all we need to understand the two basic conditions of Fc and Ft, as we already discussed in the previous slide. Fc and Ft, say this one. This one is Fc, this one is Ft. First of all we need to find out these two force using the formula Fc 0.36 FCK BFDF and Ft that is 0.87 Fy AST. Now coming over here, Now, talking about the first case, if FC is greater than FT, we have already discussed in the previous slide, if FC is greater than FT, then neutral axis will lies in flange. So ultimately we can find out moment of resistance of the beam using the concept of singly arch beam. Now XU can be find out using this formula, which is given in IS 456 on the page number 96, clause number G 1.1a. XU equals to 0.87 F5 AST upon 0.36 FCK BF. Then we can, and on the value of this XU should be less than DF, and find out XU max, that is this one. It is also there in the code, the page number 70 notes. Now once we get the value of XU and XU max, we can easily find out the moment by deciding the sections of the beam, say balance section, under info section and over info section. Okay, all the moments are there. If under info section is there, then we can use the formula G1.1b, and if it is over info section or balance section, then we can use the formula G1.1c. we can find out the moment of resistance. Now this was the case of if FC is greater than FT. Now talking about the another case, that is if FC is less than FT, say this one. So for that one, neutral axis need to be found out. First of all, neutral axis will be in the wave, so we can find out the value of neutral axis XU using the formula C1 plus C2 equals to T, and the value of XU which we get should be greater than DF. If it is not greater than DF, then we can find out the new XU by replacing DF by YF. Then find out XU max, that is as per the code on page number 70 notes. Now once we get the value of XU and XU max, as I already said, there are three possibility of the section. First one, that is if XU equals to XU max, balance section, XU less than XU max, under info section, and if XU is greater than XU max, over info section. So on the basis of these three conditions, we can find out the moment of resistance using the code. Now talking about the first condition, that is balance section. Now as per the code IS 456, if balance section comes, then we can find out moment of resistance using the two different formulas. For that one, first of all we need to find out the ratio of DF by D. If DF by D comes less or equals 0.2, then we can find out moment using clause G2.2, page number 96. While if the ratio of DF by 2 comes greater than 0.2, then we need to use the clause G2.2.1, page number 96, and moment of resistance can be easily calculated. So this is the case of balance section. At the same time, if over info section comes, then we can use the same procedure like balance section. Now talking about the other section, that is under info section. Now as per the code IS 456, clause number G2.3, page number 97, we can find out moment of resistance using two different formulas. For that one, which formulas to be used? First of all, we need to calculate the ratio of DF by XU. If DF by XU comes less or equals to 0.43, then we can use the same formula, that is clause G2.2, page number 96. And if the ratio of DF by XU comes greater than 0.43, then we can use the formula G2.2, that is the same as this case. Okay, but in both above cases, over here I have mentioned over here, in both above cases replace XU max by XU. Okay, thank you.